Deep beneath the surface of our oceans moves a hidden network of powerful currents. Invisible to the eye, yet strong enough to fundamentally influence life on Earth. Like gigantic conveyor belts, they transport oxygen, heat, salts, and nutrients across our blue planet, keeping climate and ecosystems in balance. Yet they rarely take center stage in discussions, until something goes wrong. One of the most important of these currents is the Atlantic Meridional Overturning Circulation, or AMOC. It is considered a central element of the global climate system. Scientists have been warning for years that it is not only slowing down, but could, in the worst case, collapse entirely, possibly as early as 2025. Something like this has happened in the past, but the last time was nearly 10,000 years ago. The big difference this time? We are here. How is it possible that something with such enormous consequences can remain unnoticed for so long? Should the worst occur, life on Earth would be drastically altered. It's astonishing that many people have never even heard of the AMOC. Perhaps that is exactly the problem. An invisible force that is difficult to measure and thus easily overlooked. In fact, evidence suggests that the AMOC has been weakening for 60 to 70 years, parallel to the warming of our planet. Some researchers even assume that its strength has decreased by at least 15% since 1950, and that it is now weaker than at any time in more than a millennium. One striking piece of evidence is the so-called cold blob in the North Atlantic, the only region on Earth that has cooled over the past 20 years, while everywhere else has warmed. To understand why something stops working properly, you must first understand what it is. So what exactly is this invisible force that could disrupt life on Earth? We must remember that all of the planet's oceans are connected, one single giant water system. The AMOC ensures that this system works like a gigantic mixing bowl. It transports water, heat, nutrients, dissolved gases, and even microscopic life around the globe. It is a complex network of currents and vortices that together form a massive vertical loop stretching across the entire Atlantic. These currents exist in various forms: tidal currents near the coast driven by the sun and moon, surface currents driven by the wind, and slower deep currents driven by differences in temperature and salinity. The latter are crucial here. This process is called thermohaline circulation, thermo for temperature and haline for salinity. The AMOC is part of this global conveyor belt, transporting warm surface water northward and cold deep water southward. In doing so, it brings heat and nutrients to higher latitudes, while carbon is transported into the deep ocean. The cycle begins at the east coast of North America, where the Gulf Stream, part of the AMOC, carries warm water from Florida to Newfoundland. From there, the water flows toward Europe and the Norwegian Sea. In the subpolar regions near Greenland, it cools, releases heat to the atmosphere, and forms more ice. Salt remains behind, making the water denser. It then sinks to depths of 2,000 to 3,000 meters and flows back south. This sinking is the overturning effect of the AMOC. Cold water sinks and rises again elsewhere, warming up, a cycle much like a heating system at home. Every second, it moves 17 million cubic meters of water, equivalent to 7,000 Olympic swimming pools, and transports 1.2 petawatts of heat, 100,000 times more than all the energy humans produce. As impressive as this sounds, the entire process runs remarkably slowly. A single parcel of water needs about 1,000 years to complete the full cycle. And this is exactly the problem. The AMOC is slowing down. Before we continue, a quick clarification. The Gulf Stream is part of the AMOC, but not the same thing. It is like an organ without which the system cannot live. The Gulf Stream originates at the tip of Florida, follows the east coast of North America, and then moves toward Europe. It ensures that Western Europe is much warmer than it would otherwise be. Without it, England would be 3 to 4 degrees colder, and parts of the continent up to 10 degrees colder. The Gulf Stream is part of a larger system of vortices and strong winds, a so-called ocean gyre.
There are 5 of these worldwide: the North Atlantic, South Atlantic, North Pacific, South Pacific, and Indian Ocean gyres. Due to its location, the Gulf Stream belongs to the North Atlantic gyre. It acts like a fast highway, transporting warm water from the south to the north before distributing it into smaller pathways that continue toward higher latitudes. Now that we understand the currents better, we turn our attention back to the AMOC, and particularly to how climate change affects it. Everything on Earth is interconnected, and this case is no exception. Remember the large cold blob, the only region that cooled over the last 20 years? This signal penetrates down to 2,000 meters and is a clear indication of a weakened AMOC. Temperatures are not only dropping there, salinity is also decreasing. Salinity is now lower than at any time since measurements began 120 years ago. This reduces the density of the water and makes it much harder for it to sink and merge with the cold, deep currents. One of the main causes is the increasing influx of meltwater from ice, triggered by rising greenhouse gas emissions. Several studies using advanced climate models have confirmed that the cooling in the North Atlantic is due to human influences, particularly the decline in heat transport by the oceans. A crucial key lies in the traces of the past. Climate archives such as ice cores in marine sediments reveal information about past temperatures and currents. Analyses of this data point to a long-term weakening of the AMOC since the mid-20th century, precisely when human-driven warming increased dramatically. All of these changes, rising greenhouse gases, an accelerated water cycle, Arctic amplification, lead to more extreme weather events, more floods, more droughts, heavier rainfall in high latitudes, and stronger evaporation in the subtropics. And all of this happens before we even consider the rapid melting of Greenland. Greenland loses around 270 billion tons of ice every year. This meltwater dilutes the salinity of the North Atlantic, a process known as the salt advection feedback. This very feedback can trigger a tipping point that drastically slows down or even collapses the AMOC. As early as 1961, U.S. oceanographer Henry Stommel recognized that Atlantic salinity is a tipping point for the AMOC. The system works because the water in the North Atlantic is salty, and it stays salty because the AMOC works, a classic feedback mechanism that also works in reverse. If fresh water dilutes the North Atlantic, density decreases, the current weakens, and even less salt enters the region. The downward trend reinforces itself. The past makes this even more interesting. The AMOC has never been truly stable. In Earth's history, it has collapsed multiple times, each event triggering extreme climate changes. We are still in an ice age, albeit in a warm phase, and even during past glacial periods, the climate fluctuated dramatically. Evidence comes from so-called Dansgaard-Oeschger events, abrupt warming phases followed by slow cooling during the last ice age. Many researchers interpret them as signs of an unstable AMOC. Also during the Younger Dryas, about 12,000 years ago, the AMOC slowed dramatically, likely caused by enormous icebergs drifting into the North Atlantic as the Laurentide ice sheet melted. The so-called Heinrich events were periods when massive ice sheets released large amounts of fresh water into the North Atlantic. Evidence can be found in marine sediments containing coarse grains from land. These layers indicate both an increase in icebergs and a southward expansion of cold polar waters. Scientists believe that this freshwater influx reduced ocean salinity, slowing deepwater formation and weakening the AMOC. Since thermohaling circulation is critical for heat transport to the north, this slowdown led to significant cooling in the North Atlantic. As freshwater input declined, the system gradually recovered. Salinity increased, deepwater formation resumed, and the climate partially stabilized.
The big question now is, when will the AMOC collapse? The key word is when because numerous studies reach different conclusions, but all agree if we continue as we are, it is no longer a question of if, but only when. A few years ago, the IPCC estimated the probability of crossing the tipping point this century at less than 10%. But in the latest 6 assessment report, the IPCC states that even in a low-emission scenario, the AMOC could weaken by 4% to 46% by 2100. In a high-emission scenario, the decline is between 17% and 55%. At the same time, some studies consider a possible collapse as early as 2025. So who is right? The core of the problem lies in how the AMOC is modeled and which physical processes are included. Beyond paleoclimate data, we do not yet have a sufficiently long observational record. The IPCC relied on CMIP-6, a collection of nearly 100 climate models from 49 research groups. Critics argue that the AMOC is set too stable in these simulations, underestimating the risk. Other studies, however, predict with 95% confidence a collapse between 2025 and 2095. In the end, the 2050s appear in many analyses as the most likely period. To prevent a collapse, there is only one clear answer: we must drastically slow global warming. A collapse of the AMOC would not only affect Europe. Sea levels in the Atlantic could rise by up to 70 centimeters, flooding many coastal cities worldwide. Researchers also expect the tropical rain belt to shift southward, meaning droughts in some regions and floods in others. The Amazon region, the Sahel, and Asian monsoons would undergo massive changes. As the northern hemisphere cools, the southern hemisphere would warm further. In the tropics, temperatures could rise dramatically. At the same time, the ocean's ability to absorb CO2 would decrease significantly as deep water formation weakens. Some might argue that cooling in certain regions could offset global warming, but in reality, nowhere would benefit. Climate averages are misleading. Seasonal differences and short-term extremes matter. If Scandinavia cools while southern Europe warms, stronger contrasts arise, severely impacting agriculture and infrastructure.
There is another hypothesis regarding the Amazon. A slowing AMOC could initially bring more rain and lower temperatures, delaying the transition to a savanna-like landscape. But this effect would be temporary. If global warming surpasses a critical threshold before an AMOC collapse, the rainforest could irreversibly tip. How do scientists observe this giant mechanism? With measuring instruments anchored to cables in the North and South Atlantic, so-called moorings, they record current speed, salinity, temperature, and other parameters. The UK-led RAPID and OSNAP programs have monitored the AMOC since 2004. A strong decline in winter deep-water mixing could be an early warning signal. And the last question? If the AMOC has collapsed and returned in the past, could that happen again? Models show that the system exhibits hysteresis. Once a threshold is crossed, it does not easily return to its original state. Studies by the UK Met Office suggest that the AMOC can recover if freshwater input stops after 20 years, but not after 50 years. This implies a resilience window of 20 to 50 years. However, today's situation is unprecedented due to extremely high CO2 concentrations. The bottom line? A collapse in 2025 is highly unlikely. The IPCC's estimates for the end of the century seem too optimistic. The 2050s emerge as a particularly critical decade. And the solution? It couldn't be clearer. We must significantly slow global warming. Climate change shows itself not only in droughts, storms, or melting ice, but also in invisible processes like the AMOC, processes that can fundamentally affect our lives. Earth has recovered from such events in the past, but this time a highly advanced civilization lives on it. The planet will survive. Humanity, at least in the form we know it, may not.
Thank you very much for watching to this point. If you subscribe and leave a like, you really support us a lot.